Have you ever wondered how our electronic devices work? From smartphones to laptops, these gadgets rely on tiny components called transistors. Transistors are the building blocks of modern technology, quietly working behind the scenes. Transistors are incredibly small, often microscopic in size, yet they have revolutionized the way we live, work, and communicate. In this video, we will embark on a journey to understand these tiny wonders. We will explore what transistors are, how they work, and their profound impact on our lives. Get ready to delve into the fascinating world of electronics. We will uncover the secrets of transistors and their crucial role in shaping our modern world. Prepare to be amazed by the power and versatility of these miniature marvels. Imagine a valve controlling the flow of water. This valve can be turned to allow more water to flow through, or it can be tightened to reduce the flow. In some cases, it can be completely closed to stop the water altogether. You can adjust the valve to increase, decrease, or completely block the water flow. This simple mechanism allows us to control the water pressure and flow rate in our homes and industries. A transistor works in a similar way, but instead of water, it controls the flow of electricity. Just like the valve, a transistor can regulate the amount of electrical current that passes through it. A transistor is like a tiny switch that can turn electricity on and off. When the switch is on, electricity flows freely. When it's off, the flow is stopped. This on-off capability is fundamental to how transistors operate, but it's much more than just a simple switch. Transistors can also act as amplifiers, which means they can take a small electrical signal and make it much larger. It can also amplify electrical signals, making them stronger. This amplification is crucial in many electronic devices, allowing weak signals to be boosted to usable levels. Think of it as a megaphone for electricity. Just as a megaphone amplifies your voice, a transistor amplifies electrical signals. Transistors are made from special materials called semiconductors. These materials have properties that are between those of a conductor and an insulator, making them perfect for controlling electrical currents. These materials have unique properties that allow them to control the flow of electrons. By manipulating these properties, we can create devices that precisely control electrical currents. By applying a small voltage or current to one part of the transistor, we can control a much larger current flowing through another part. This ability to control large currents with small inputs is what makes transistors so powerful. This ability to control electricity with precision and speed makes transistors incredibly useful. They can switch on and off millions of times per second, enabling the fast processing speeds required in modern electronics. They are the fundamental building blocks of countless electronic devices, from simple calculators to complex computers. Without transistors, the digital age as we know it would not be possible. In the next section, we'll explore the different types of transistors and how they differ in their structure and operation. Each type has its own unique characteristics and applications, making them suitable for various tasks in electronics. Bipolar junction transistors, BJTs, are like the workhorses of the transistor world. They are fundamental components in modern electronics, playing a crucial role in a wide range of applications. Whether you're listening to music on your headphones, watching a movie on your TV, or even driving a car, BJTs are likely at work behind the scenes. They are widely used in various applications, from amplifying audio signals to controlling motors. In audio amplifiers, BJTs help boost weak audio signals to drive speakers, providing the sound we hear. In motor control circuits, they regulate the power supplied to motors, ensuring smooth and efficient operation. BJTs come in two main flavors, NPN and PNP. These two types of transistors are distinguished by the arrangement of their semiconductor materials and the direction of current flow within them. Understanding the differences between NPN and PNP transistors is essential for anyone working with electronic circuits. Don't let these acronyms intimidate you. They simply represent the arrangement of semiconductor materials within the transistor. The letters N and P refer to the type of charge carriers that dominate in each region of the transistor. N-type materials have an abundance of electrons, while P-type materials have an abundance of holes, which are essentially the absence of electrons. An NPN transistor is like a sandwich with a layer of P-type semiconductor sandwiched between two layers of N-type semiconductor. This structure allows the NPN transistor to conduct current when a small voltage is applied to the base terminal, enabling the flow of electrons from the emitter to the collector. The N stands for negative charge carriers, electrons, and the P stands for positive charge carriers, holes. In an NPN transistor, the electrons are the primary charge carriers, moving from the emitter to the collector when the base emitter junction is forward biased. Think of holes as empty spaces where electrons want to go. When an electron moves into a hole, it effectively fills that space, allowing current to flow. This movement of electrons in holes is what enables the transistor to function as a switch or amplifier. On the other hand, a PNP transistor has a layer of N-type semiconductors sandwiched between two layers of P-type semiconductor. This arrangement causes the current flow to be opposite to that in an NPN transistor, with holes being the primary charge carriers. The current flow in a PNP transistor is opposite to that in an NPN transistor. In a PNP transistor, the current flows from the emitter to the collector when the base emitter junction is forward biased, with holes moving from the emitter to the collector. Instead of electrons, holes are the primary charge carriers in a PNP transistor. This difference in charge carriers and current flow direction is what sets NPN and PNP transistors apart, making each type suitable for different applications in electronic circuits. Both NPN and PNP transistors have three terminals: base, collector, and emitter. The base terminal controls the transistor's operation, while the collector and emitter terminals are where the main current flows. By applying a small current to the base terminal, we can control a much larger current flowing between the collector and emitter terminals. This ability to control large currents with small ones is what makes BJTs so powerful and versatile in electronic circuits. This current amplification property makes BJTs ideal for amplifying weak signals. Whether it's boosting audio signals in a speaker system or amplifying radio signals in a communication device, BJTs are indispensable in modern electronics. Their ability to switch and amplify signals efficiently makes them a cornerstone of electronic design. While BJTs, or bipolar junction transistors, are like the dependable workhorses of the electronics world, having been around since the mid-20th century and used in countless applications from radios to early computers, metal oxide semiconductor field effect transistors, or MOSFETs, are like the nimble athletes of the transistor world. They are designed to be fast, efficient, and highly responsive, much like a sprinter on the track. MOSFETs are known for their high speed, low power consumption, and compact size. These characteristics make them ideal for modern electronics, where space and energy efficiency are paramount. They have become the dominant type of transistor in modern integrated circuits, powering our smartphones, computers, and a myriad of other electronic devices that we rely on daily. From the moment we wake up and check our phones, to the computers we use at work, and even the smart devices in our homes, MOSFETs are at the heart of these technologies, enabling them to function efficiently and reliably. Unlike BJTs, which rely on the movement of both electrons and holes, MOSFETs have a unique structure that allows them to control current flow using an electric field. This fundamental difference is what gives MOSFETs their superior performance in many applications. A MOSFET has three terminals: the gate, the source, and the drain. These terminals play crucial roles in the operation of the transistor. The source terminal is where the current enters the MOSFET, and the drain terminal is where the current exits. The gate terminal, on the other hand, is used to control the flow of current between the source and drain. The gate terminal is insulated from the conducting channel between the source and drain terminals by a thin layer of insulating material, typically silicon dioxide. This insulation is critical as it allows the gate to control the current flow without direct contact. Think of the gate terminal as a tiny paddle hovering above a stream of water. By adjusting the position of the paddle, you can control the flow of water beneath it. Similarly, by applying a voltage to the gate, we can create an electric field that either attracts or repels the electrons in the channel, effectively controlling the flow of current between the source and drain. This ability to precisely control current flow is what makes MOSFETs so powerful and versatile in electronic circuits. In a MOSFET, the voltage applied to the gate controls the flow of current between the source and drain terminals. This is akin to how a valve controls the flow of water in a pipe. MOSFETs are incredibly versatile and come in various flavors, including N-channel and P-channel MOSFETs. Each type has its unique characteristics and is suited for different applications. In these circuits, MOSFETs can turn on and off millions of times per second, enabling the high-speed data processing that is essential for modern computing and communication technologies. Whether it's in the processors of our computers, the memory chips in our smartphones, or the power management systems in our electric vehicles, MOSFETs are the unsung heroes that make it all possible. Their efficiency, speed, and versatility continue to drive innovation in the electronics industry, shaping the future of technology.